The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we will hopefully by end of the class we will show you a histogram for the quiz. We are very happy you guys did really well. So we feel like actually you learned something on the quiz. So it makes us happy. So then we're hoping to have the histogram ready by now, but we don't. By the end of the class, hopefully we'll take a break in the middle and go through the histogram. So we are going a little bit off from regular programming. If you look at the class schedule, we are going to have a guest lecture today, but I am the guest lecturer, I guess. So I'm going to talk about what compilers can and cannot do, because as you went on last couple of projects, you tried hard to do weird things out of the compiler, create different pieces of code, hand unroll programs. And so I'm going to kind of first walk through some stuff that is very practical, what the current GCC do or don't do. Okay, so we'll just go through some stuff which is interesting. And then I'm going to, so yes, let's get the outline first. Okay, this doesn't work. Okay. Then we will talk a little bit about where normally optimizations happen. What are all the possibilities? Just very quickly to give you a feel, it's not all static time compilation. And then go through two things. One is data flow analysis and optimization. That's a big part what compilers does. And then also instruction scheduling. Instruction scheduling might not be that important on a superscaler, but it's always good to know what it does, because there are some cases where you have to do it in the compiler, the hardware cannot do. So we'll look at some of those cases. So the first thing that we found a lot of you guys did is you try to inline a lot of code when you wrote in your projects. And in fact, one way to do that is to do a macro. Macro is basically make sure that it definitely get inline, but macros are ugly. You can't, there are many things you can't really do with a macro. The other thing is we can actually do a simple max calculation using a function, okay, static function defined. And the first one is calling this one, second one is calling this one. So what do you think this is going to do? How many people think that the code produced between this and this is going to be drastically different? Code produced for this function versus this function going to be drastically different. Okay, or different. Okay, some people think code produced is going to be different. Okay, why do you think it's different?
Well, so the second function calls the first function, and the first one, the third one calls the second.
Yes.
So since you have the first one calling max1, which is a macro,
yes,
the compiler would just copy and paste
yes.
that there.
Okay. Okay.
Whereas the second one, it will try to actually optimize wouldn't it try to optimize what is inside UN64 and
okay.
do something on it?
So what he thinks is that this is just going to get copied. This will be still a function called try and do some optimization. In fact, what it will do is the first function is going to get inline. Something interesting here, what you see is even though there's a condition here, there's no branch. They have this cmove instruction that basically can be used to do a conditional move. So instead of having a branch and having pipeline stalls, this managed to convert this into a nice direct call. The interesting thing is the second one is also identical. So what it did was it said, I know this function, I can inline. It got inline automatically. You didn't tell it to do, the compiler will actually inline it for you, and then did all the things that are necessary. So what that means is you don't have to write some of these like ugly macros and hand inline. You can have nice functions in there, especially if it fits in the same file, it will get inline. Of course, if you define it in a different file and this file doesn't have access to it, it won't. But if it is in the same file, it will get inline. So you get the same result. So you can still have this nice abstraction. You don't have to deal with optimizations at that level. So another thing is we had this entire question.
So on the previous slide, other than looking at the assembly code, how do we know when the compiler makes this call out?
Look at the assembly code. So, question.
Why do you prefer like the static versus the
So the reason I did static is basically I want to make sure it's not visible outside the file. So if you don't make it static, what will happen is everybody else has the visibility and then you kind of pollute the space with a lot of names. So if you keep static, it's only within you. If I had inline, I could ask him to forcefully do that. But what I'm showing is you don't even have to say inline. It will inline by itself. Question?
More of a comment. You can also use gproof to see which functions are being inlined without actually looking at the code.
Okay, when you have gprof, actually gprof, what will happen is the file will vanish for gprof, isn't it? File will vanish because the function will vanish because gprof will basically, if you have a function, you go look, you don't see the function. And it might give even a bad impression that, okay, that function is not important. So that you have to be careful in that. Because when you look at gprof, you will see some files, the inline some functions, inline function won't be there. And am I right, or is it doing anything interesting with the simples? No. So I think it will just vanish, and they say, oh yeah, that function is not important, but in fact, it might be really important, but it got inline. So that's one way to a little bit worry about. Does it make sense? Okay. So we learned bit hacks. So it was really fun. We are learning all these interesting bit hacks. But the interesting thing is, in fact, your GCC compiler also knows a lot of bit hacks. So it's also a pretty smart compiler. So if you have something like this, what do you think the assembly would be? Yeah, it actually did this one. This is very interesting to say. What it did was it didn't do shift. It did this load effective address quad instruction, LEAQ instruction. What it does is multiply these two, and it's add. It does nothing in here to add, and then it can add a constant. So this very complex address mode that is being used for completely different purpose. So this is pretty sacrilegious. It doesn't use as address. It's doing this multiplied by this. There's nothing to add. There's no offset to add. Save it here. So the reason, so it's actually doing this multiply, but the nice thing is it doesn't affect any things like condition codes and stuff like that. So this is a fast thing to do. Okay. So we said, okay, that's it. That's interesting. How about multiply by 43? Okay, that makes it a little bit more complicated. What do you think? How do you multiply something by 43? Anybody want to take a guess? What's the easiest way to multiply 43 than saying mul 43?
Multiply by 32, add that to multiply by...
So it did something interesting. So here's what it did. I want you guys to stare at it a little bit and see whether you can even figure out what's going on here, because this is kind of funky. So what happens after the first LEAQ? What's in RAX? What's in RAX after first LEAQ instruction? And you want to take a wild guess? Five. Yes, exactly. What it does is it's 4a plus a, because this is a plus a, 5a in here. And then after here, what happens? Four times this one plus this one. Yeah, it's 21, because 4 times this is 20, and you add the original RX 21 here, 21. And then you do this time again 42 and add another 143. So it did all these interesting 3 instructions to get to 43. And so this is fun. You can spend days giving different integers and see what the compiler generates. And also at some point see when does it give up. And it doesn't give up for a while. It starts creating some crazy things. Okay, try one more thing. Okay, this has to be hard. 254. How do you get to 254? There's no easy way to do that. How did that do that? They did a very interesting thing in here. So I will show you this one. So here's that instructions it generated. So what it did was, it's doing here getting a two-way by doing LEAQ because it didn't give since it didn't give a multiply, it just multiplied by 1. So it's just adding these two, get two-way. Okay. And then it adds, multiply by 128 by doing a bit shift here. And then it goes to 256. Why did it do this instead of doing one instruction to 256? Yeah, then it went and subtracted the 2a again and got 254. So it went overshot, subtract, and subtract one also got calculated here. It has a really smart way, I don't know what complex logic is there, to basically figure out these combinations of instructions that can do multiplication. We played around a bunch of things until we ran into a couple of thousand. It was doing these weird patterns after a couple of thousand, especially if it is too close to 2 to the power, it can easily find it. Even primes it managed to find. Actually, we give a prime and it found it because you found the closest thing, add a couple of things to it, and you can get to the prime. So it's kind of interesting how far it goes in just eliminating multiplies.
Why doesn't it just go about it? It says 3 so 2a.
So this is a very interesting question. So what it's doing is, it has realized somehow that doing a direct multiply by 254 is going to be slower. So the multiply instruction, if you go, I think you can also look at multiply instruction, how many cycles it's going to take to
I mean, why doesn't it 6?
Oh, because if it needs to get this 2a again. So it gets to use the 2a. So by calculating that, it kept it. I don't know, you might be right, because if you do 286 and 2a, then there's no dependence chain here. Right now, there's a dependent chain here.
Yeah, would it be conceivable?
Yeah.
Multiply 56 and subtract self by twice?
Twice, yeah, something like that. Or calculate this separately, 2a and 256, and then add and subtract them. Might be interesting. So there are other ways of doing that. So in fact, I don't know, it might be because of a register copy in here. I don't know why they didn't do that. But it's thinking. It's look at all the instructions, sequence, how long it's going to take, and it finds this interesting sequence. So sometimes when you're looking at your optimized code, they will look like something crazy that you can't read because it does things like this. So you found like a simple multiply somewhere and end up with a piece of code like this. And so you need to kind of decipher saying what's going on backwards. So that's why reading assembly is sometimes hard, especially optimized assembly. Okay, so I did absolute value, and look, it did the bit hack we basically learned in class. You can go look at that. This is the entire thing that Charles talked about to find absolute value. It knew that, so it has attended Charles's lecture, at least the GCC programmer. Okay, so here's an interesting thing. So what I did was I am doing update. And I have this big large array here, and I'm checking the index to be within 0 and this value before I update it, because I don't want to write out of bounds of this array. Okay, makes sense, because I want to make sure that I write within the bounds. Interesting thing here is I am doing 2 checks here. I end up doing only 1 check here. What happened to my other check?
How big was the array and put like a sentinel value at the end?
No, it's doing something a lot more simpler. So to give you a hint, this is a signed value, and I am doing unsigned compare. What happens if the value is smaller than 0? A signed value is smaller than 0 is what it is like in unsigned. It's a huge number. It has to be bigger than this one. So because of that, it can just say, okay, look, I don't have to check that. I can do unsigned compare, and I will get anything less than 0 also in there. So one more thing, before I continue with this one. So if I actually put it in a loop, and say I'm going to iterate to I to this value in here. Then what it will do is at that point it will inline this, and then it can completely eliminate the check. It will know that in fact my bound is going from 0 to this one, so I don't have to check the bound. So what this did was this inline this function in here and completely get rid of the checks completely. And this is basically branch condition in here, because it said, okay, look, these things are redundant because I know, because I'm iterating from this to this value, these bounds will be always met. So it is smart in that. Do you see this? How this is going? Cool stuff the compiler do. So this is why compilers are smart, when they are smart. And the interesting thing is, here's another one. So now 0 I could imagine, because less than 0 I can do that. How about if I am checking from 5 to 1000? So it generated this funky code. It subtracted a 6 here in the value, and then checked for 993 instead of 1000, because it kind of shifted the value to 0 basis basically. And then you can check that thing, and then you can basically got 2 conditions down to 1. See, the thing is there are many places where bound checks is very important. Okay, if you are doing a lot of array computation, stuff like that, if you don't want to have buffer overflows and stuff, you want to put bound checks. And so optimizing bound checks is a very important thing. So having these kind of things can, in many programs, probably will give good performance. So that's why compilers are really good at and spend time trying to do bound checks. So this is kind of an interesting way of doing that. So the next thing I want to look at is vectorization, because all these machines we have this SSE instructions that can run really fast, and you probably saw it in there, and see what kind of code it get produced after doing something like that. So here's a simple program. Oops. So I have 2 arrays, and I'm just copying A to B. Okay, something very simple. And also the other thing to note is I know exactly from where to where I'm copying, and I also know which arrays I'm copying. So when you look at it, it produces a cool code like this. So what it's doing is it's basically making EAX0 here by doing XOR. And then basically moving the value A into the XMM registers much larger, instead of having a character, 16 of them, and copying it back into B. So basically you are doing copy in here, and increment by 16. By now every iteration you are copying 16 of them. Why could I just be done with just putting this small piece of code? What additional information this is taking advantage of?
Does it know that like n is like multiple? Like
Yes,
you can actually put
exactly. Because it knows that it goes from 0 to this value. In fact, it knows it's a multiple of 16. So it knows that. That's why it just have to do that. It knows exactly, and these things are nicely aligned to the boundaries, word boundaries. So it knows that. So I can read that, and I know all those facts, and that is why I can do this computation. So now, instead of doing that, I did one simple change. Instead of going from value, I went to n. 0 to n. I know where it starts, and I know where it's ending is somewhere at n. I don't know where the end is. Okay. Then this has to do something a little bit difficult. So the code produced looks like this, because now I'm not going to go through this code. The only thing to say is this is actually doing still the MMX instructions. But it's to make sure that because n, it might not be a multiple of 16, you have to take care of the final number of iterations outside that. So you have to go up to the multiple and then basically do a normal loop one at a time. So it produces a little bit of a more complicated piece like that. So that's what compiler has to do. And so then we have a piece of code like this. Oops, what happened? Okay. So the interesting thing here is now I created basically a function where it's not A and B. I'm getting 2 arrays as arguments, and then I'm giving a size to copy, and I'm copying that. And now I have an extremely complicated thing that's getting generated. Why is it complicated? What do I have to know when I get this function to make sure that first of all, it's still doing XMM somewhere in here. Okay? What that means is it's trying to do this very fast copy of multimedia using multimedia instructions. But what else can happen in this function? Because compile has to deal with all the cases. What are the other cases it has to deal with? May not be aligned. Because, for example, because this XMM assumes that they are the word boundaries. When you read 16 bytes, you assume it's aligned to 16-byte boundary. It might not be aligned because you have no idea what these two are coming from. So that's one thing is they might not be aligned. What else?
They don't even have to be the same length. Because, I mean, that thing could just be copying up to n.
Yes.
But it might just be copying partially parts of the array. They don't have
yeah, that's true. So what that means is because arrays could be led, but arrays is somewhere in the memory. Just you give 2 pointers to starting point. That is what x and y are. There are 2 starting points somewhere in memory and start copying in there. So what else can happen because of that? Because in A and B, we knew there were 2 separate arrays. What else can happen? Back there. Yes, so arrays can start to overlap. And if arrays are overlapping, that you might be end up in an interesting situation. So you have to figure out whether arrays are overlapping, whether they are aligned. Actually, there are 2 types of align. One is self-aligning. So assume we took these arrays and start copying from the byte 3. So then what you know is basically byte 3 to 16 is not aligned. You can't start copying chunks in there. So you run byte 3, but when you run up to 16th iteration or 13 iterations, then you end up in again aligned chunks. So if that case, you just run some preamble to a first aligned place, and then you go to aligned chunks. But if this is starting at 3, this is starting at 8, then they are never going to be aligned. The things are copying A and B are not aligned, so then you have to treat it differently. And then so there's a lot of different cases you have to do. So if you just give something like this, the problem is the compiler has to deal with these thousands of different cases, and in this one, since this is small, it probably thought through all the possible cases and generated it. So it's dealing with all those things, checking out everything and trying to find the optimal case and do that fast, hoping that you get optimal case most. But if you have something more complicated, the compiler won't be able to do all those things, so it might give up. So the interesting thing to here note is more information to give to the compiler, it's better. And here compiler has to derive a lot of things, but probably not happen. Another interesting thing is now, the first one I just copied 2 arrays A to B. In memcopy 4, I just called memcopy 3 by doing same thing, A to B, copy 1024 elements. This is the beauty of inlining. So what it did was, in memcopy 4, it inlined memcopy 3 and substitute x and y to A and B and n to 1024. And it realized that it doesn't have to do all these tests like it did. What it generated is very close to what we got here. Because after inlining, it realized, wait a minute, I'm copying A to B, I know where the start, I know where the end, I know the size, I know every these things, and I don't have to do any of these things. I can actually generate this very simple piece of code. So I think that is a neat thing. So what that means is what this shows you is, in fact, if you can build these general functions, things in there, and then you can call them, and if it is done right, the inlining will basically do all the optimization. So you don't have to have 50 different mem copies for all the different things in your code. Okay, you wrote a general function, and you call it in a way it can get inline and got the as efficient as possible as hand optimization. Okay, so this is, I think it's a really interesting thing. And what this tells you is in your, when you're doing projects, you don't have to do all these very complex in small functions, hand inline, stuff like that. But it's always good to check that, in fact, the compiler is doing that, because you don't know. You assume the compiler is doing that, and there might be cases it might not be. And I will show you one example here. So I want you guys to look at this function a little bit. Okay? I am doing 2 mem copies. I am copying 1024 elements. One I am doing AI plus 1, A into, this is xy, this is x. get copied into Y, AI plus 1 to A. So that means I have array like that. Array like this. I am giving AI plus 1 as the source. I am giving this is the source. And I am giving this as the destination. Okay, what does this copy do? I'm copying 1024 elements. So the first one, this one will copy to here. Second iteration, this will get copied to here. Third iteration, this will get copied to here. What does it do? Yeah, I just do a one left shift of the array. Okay. My second example, I give this as my first element, this as my source, this as my destination. What happens here? Exactly. All of them could copy the same number. Okay? So now, if you look at the code that's being produced, okay? So the interesting thing here is it realizes in this one, I can still do MMX. Because I can still copy, take a chunk and copy it one back, take a chunk and copy it one back, take a chunk and copy it one back. Okay, do you see that? But what does the next one do? It uses MMX instead. What does this one do? Copying something from DL. Move B DL array, X where's DL? Read, where's DL? Is this, you just copied this one? Huh. I hope I copied it properly. That doesn't make it look right to me. So this is interesting. So I might have missed the instruction. I think it takes a, This doesn't look right, is it?
So what's A then? It's char, I see. It's 1 byte.
Yeah, 1 byte.
Yeah, no, so what it's doing is just taking the first byte and then just moving it
Into EDX.
into EDX.
Oh, right. This is actually doing the right thing. This is doing the right thing. So what it does is this move this one into EDX, entire thing, and then this gets the DL is get the first byte out of EDX. Do you see what's happening here? So the A gets into EDX, first byte get it, then got the first byte out in here, and then you keep copying that byte one at a time to this location.
So it's not smart enough to do it.
So this is where we find something interesting in the compiler. So what's doing is in here, you are copying this data, word around here into this, byte into EDX. Okay, so DL is the first byte out of EDL. That's byte because what? Yes, because in x86 address streams, you do R in a 32E, R64E32, and just DL is just first byte in there, lower byte, but D low byte of that. DH is the higher byte. Because this byte gets copied into everything here. So do you see that? This byte is the one that, because that's what happens when this copy is basically this byte got everything else got replaced by this first byte in here, copied in here, in there, and then it just goes around copying it in here. So actually I did it in this way. So what I did was basically went from 1 to 1025. AI equals A0. This is basically what happened. So 1 to 1025, I got A0. And then basically that's what happens in here, same thing here. Okay? Do you see what's going on? But I just did something recent. So assume I'm not using A0, it's doing right here. What happens? I just use something else. I use B0. So shouldn't it should be the same, isn't it? If I use B0 here, instead of doing A RIP, this should be B RIP, isn't it?
Sorry, where's B0 defined?
Here. It's a different array. Oh, I didn't put it here. It's a different array. So instead of A0 here, I put another array in B0 here. Does it matter whether it's A0 or B0? B0 is a different array. It shouldn't matter because it's a different array, different element that you don't do that. But the interesting thing is if you do that, it managed to convert it into MMX. So this is where the compiler is basically falling short a little bit because it could have done this for these two. Okay, it's the same thing because what it does is it takes this one element from here and copy it everywhere. I could have done it, but for some reason the compiler decided if using a different array, B0, I can do it, but I'm doing A0, I can't. Even though these two is basically identical, except these are different. I'm not doing any kind of overlap, anything. Question?
Wait, doesn't like larger sizes?
Yes. So what it does is, when you go somewhere, it's doing pack. This the pack instructions in here. What it does is it takes that byte and it kind of makes multiple copies of the bytes and create a larger copy in there, 16 copies in there, and then it can kind of stamp it everywhere. So what it's doing, it's copying A0 multiple times, one at a time slowly. So what this does is it takes a B0, make copies, 16 copies in there, in registers, not in memory. I created like a template of 16 and I kind of stamp it as I go.
It's probably a failure of its alias analysis.
Yeah, it's failure somewhere. So this is where the compiler does some magic, kind of very complex things in here. But somewhere in the compiler it failed. So what you want in here is a code looking like this. But it produces this one. So this is where the compilers are great. It does some amazing things. But it's not infallible. It can do, there might be corner cases that its analysis fails. So that's why it's always good, even though you can take advantage of the compiler to look at what's generating. And sometimes when you tweak around it, you suddenly realize, wait a minute, I can get the compiler to do something better. And then you can say, wait a minute, now how do I work myself back? Sometimes you end up changing your C code a little bit, like the examples the TA showed when they're doing their demo, that if you tweak a little, you can actually get the compiler to do that instead of trying to do these things by hand. Excuse me. So the compilers are powerful, but you have to be careful. Another interesting thing is, here's factorial. So normal factorial is basically you have call a function call with x minus 1 and multiply by x. But you know function calls are very expensive. And in fact, GCC knows that too. So what GCC did, it basically eliminated the function call and converted into iterative function here. So the EDI got x in here. And then it goes to a loop. So it first checks whether it's 1. If it is 1, you go to the end and return it. You are done. If x is 1 or less than 1. And otherwise, it goes to a loop. It doesn't go do any function call. It just basically calculate this fact value inside EAX and keep multiplying fact iteratively. So it can take this recursive, simple recursive functions and also convert it into iterative mode. So it does some very, very fancy stuff in the compiler. So the compilers are fun when they work. But the key thing is there are many cases it doesn't work. So next, I want to switch gears. Any questions so far? Sometimes it's fun to like find breaking points in the compiler. If I use in some, this is not static. No, it won't make a difference because what it says is if it is not static, it's visible to the outside world, but within this function, it's the same. So what it does, it's kind of, I'm like limiting my pollution. So because that otherwise what happens is everybody outside will see these names and they can, so if you use that name again somewhere else, it might just use this one. Things like if you use static, it says this is within the file, nobody else should see this. So it's creating a local copy. It's kind of a poor man's class hierarchy. If you in Java, basically each file is a single class, and you make sure that things inside the class is not visible to outside. When you make static, you made it only visible within that file. So you kind of you can think about your file as your class, and so you limit the scope of the variable to within that. So some benefits of object-orientedness can be gained, I guess. But it's a static variable, it's not a class variable. Okay, why is it not? Okay, so next, before I get into doing compilers and say what compilers do, I want to give you a flavor saying there are many different places where you can do optimization. So if you look at what happens in the program first goes through compile time, compiles each file, then it links all the files together. At some point, the files will get loaded into your machine, and then it will be running. So if you do things at a compiler, you have full access to source code. It's very easy to kind of look at the high-level transformation, low-level transformation. You can look at the entire gamut of things to do. And the nice thing about compilers can be slow. Nobody's going to complain. It's not going to be part of your runtime. So you're just going to wait, but it's you, not the customer. But the problem with compilers is it doesn't see the whole program. You see a file at a time. So all these inline things and stuff has to be in the file. You can't put it in a different file and assume inline, except probably include file. So, and also don't know the runtime conditions, because at runtime it might be having different inputs, different size of load and stuff like that. I don't know any of those things. And also I don't know about the architecture. So if I compile, I have to make sure that it works on AMD machines, Intel machines, stuff like that. Of course, you can give special flags and try to compile for one machine and breaks if it runs on the other one, but you don't want to do that. So the compile has to be a lot more general, and this can be sometimes problematic. So when you go to linker, the nice thing is that this is the place you have the entire program available. Sometimes people try to do things like inlining at the link time, because that means you know everything in there. So even if it comes from a different file, I can inline it because I have access to here. And still, there might be things that's not available, like dynamically loaded classes and dynamically loaded data. Things like Java might not be available. And of course, you don't have access to source most of the time.
Sorry, what do you mean that you have the full program in the linker, because the linker is dynamically together. But so how do you say that may not have the full program? What might you not have?
So dynamically links, if you have something like Java, there might be some data that kind of get dynamically generated or dynamically linked. So when you're running, if you're running wrote to your browser, all those JavaScript classes and stuff like that you don't have access to, because those are coming in there. So there might be places, things that it gets as it runs, not in C, but in other languages. And the load is interesting time. Here, load time is important, because when you double click, you want your program to appear fast. You don't want it to take a long time. But you have kind of access to all the code in here, and you have some idea about the runtime, also the architecture and stuff like that. What you have, not the runtime, but the architecture, exactly what machines you are running. And then of course you can do at runtime. The thing about runtime is you have full knowledge of everything, it's great, but every clock cycle you spend optimizing is one clock cycle you take away from the program. So things like a Java JIT compilers, they try to do minimal things or very fast things. It can't do a lot of complicated things because it's too expensive. Okay? So we are not talking about any of these things anymore, but it's always good to know as you go about using Python or Java or JavaScript and stuff like that. See, wait a minute, where is this thing happening to my code? Because it might not be all compile time stuff. It might be happening at different stages. So you need to know who's actually mucking with your code and know that there are other people who can muck with your code. So next I want to switch into data flow analysis. So this is what compilers are good at and compilers try to do all the time. So it's basically compile time reasoning about runtime values and variables or expressions in the program at each different program point. Okay, so that means compile time I need to know, okay, at this program point, what could it be? So things like which assignment statement produce a value or variable that I'm using. Okay, if I'm using a value, who actually created that value? Or which variable contain the values that are no longer being used by somebody else. So that means I'm trying to analyze the program. And what's the range of values that each variable can have? Okay, so the key thing here is this has to be true for every possible input and every possible execution. Normally when you're running saying, and this time I know my variable value, but every possible time this has to be true. Okay, if there's a condition that something can happen, you have to make sure that condition is not going to break your program. So last thing you want from optimizer is to basically start producing different results. Even rarely, it's not good. So you want the optimizer to kind of produce the same results that you got without optimizing. And this is why this has to be conservative. So first I want to go through a little bit of example what kind of things the compiler do. You probably have seen this in one of the early lectures. We talk about some of these as hand optimizations, but I'm going to go through some of them by using this program. So here's a kind of a, it doesn't mean anything what I'm doing here. I have a loop here, I'm calculating some function in here, and then I am adding something else to this x here, and I have some initializations in here, just something that I can demonstrate what it does. So it does no meaning for this one. And here's the assembly instructions. I'm not going to go through assembly, but it will be interesting so you can actually relate and understand why this is happening in this assembly instruction. So I put assembly into 2 slides. So the first thing you can do is thing called constant propagation. So what it says is for all possible executions, if a value that has in a variable is the same and we know that value, okay, that's a constant, and I don't have to keep that value in that variable, I can replace that by the constant. Okay, and this sometimes, excuse me, sometimes when you look at data flow optimizer, you can say this is done. As a program, I will never do that. This is something you should be doing. For example, have things like constant variables, then constant values all over. But sometimes some looks dumb. But what happens is sometimes when optimization does, one optimization might lead to code that looks like that. That can lead to, I will show you something sometimes that you might not write a code that looks that dumb, but a previous optimization will leave or change the code in a way that this optimization can take advantage of. So nice thing about this is you don't need to keep values in the variables because you can free some variable, that means free some registers. Also, most of the time when you do constant propagation, it leads to additional optimizations. So in this program, what are the things that can be constant propagated? So we know x is 0, x is a constant up to this point. But since x get modified here, my data flow say, wait a minute, I am going through this loop and x is constant from here to here, but after this point x is not constant because it get modified in here. Okay, so that's what data flow is going to say. And so I can't do that x. But if I look at y become constant here. All input that goes into this loop, it has to go through here, it becomes constant in every part. And then it doesn't get modified in this loop at all. Okay, so then I can actually do constant propagation and get rid of y. Okay, so now I have a program like that. So normal compile optimization is done by pass, lot of passes get repeated multiple times. So you leave it like this. So even though this is just simple thing, but we leave it to somebody else to optimize that, which is what we call algebraic simplification. Basically, this is you go to your whatever 4th grade, 5th grade, 6th grade algebra book. I don't know where you learn, somewhere you learn algebra, I guess. And they have all these very simple rules. And like something multiply 0 is 0, multiply 1 by that, and all those rules. And then you can just basically code them up and look for these patterns and replace. And that's what the compiler does. And in fact, we look at something like this, a simple shift, but you saw before that it do much more complicated things. And it's a lot less work at runtime, and also it leads to more optimization, so it can simplify things in here. And other thing is, sometimes this algebraic simplification can do weird things. If you want exact precise stuff. For example, if you're doing floating point. Because floating point, A plus B plus C is not A plus B plus C, or B plus C plus A are different, because you can get small teeny differences in here, in these kind of, if you violate commutativity and associativity. And some people care, most people don't, because it's like so small, most people say I don't care, others do. And also sometimes when you do this optimization, things like overflow and underflow that happens. Because if I do x plus x minus x, or x is very large, x plus x minus overflow, and then you don't end up doing minus x because it overflows. But you said, oh, x plus x minus x is just x. You don't overflow anymore. So you have changed the behavior of the program. But most of the time compilers think that things like that are special cases. They are not the normal behavior, so changing them is probably okay. So otherwise you can't do anything. So now here, what are the algebraic simplifications I can do? Excuse me. What can I do here? Yeah, I multiply by 0. I can just get rid of this, that, and 0, I leave it here, and then there's another algebraic simplification, I can do that. But now I am leaving it here, because there's no algebraic simplification. X equals x there's nothing you can do. That's called copy propagation. Copy propagation says you are just making a copy of one value to another, just get rid of the copy. You don't need to do a copy. Very simple thing here. Less instructions, less memory registers because you are not copying. However, when we come to register allocation, I will talk basically, if I use the same register now, I might have things that was in 2 registers, x copied to y, now is all in x. So that means I might have some variable in a register that you call my interference graph. I will talk about this in a little while, so I'm just forward referencing. That might not be easily register allocatable. And so in here x equals x, I can get rid of that. And another interesting thing is common sub-expression elimination. If you do the same thing multiple times, you calculate it once, less computation. Cons is you need to keep this result somewhere between the 2 users. So if I have too many of these things, I might just run out of registers to keep these values calculated. And also interesting thing is this can hinder things like parallelization. When we get there, we can see that by adding additional dependencies in there. So in here, what are the common expressions? Either you guys are bored or the slide is way too hard. You're bored? I plus 1. Okay, good. So there's I plus 1 in here, and I can calculate it once, and then I can just do the multiplication of that and do that. And voila, I got rid of 2 addition and multiplication to 1 addition and 1 multiplication. Okay. Next thing is dead code elimination. So if you are doing something that nobody is using the value, why do you do it? And less computation, and maybe relay storage because you're not storing these values, you're computing, and that's really nice. And there's not much of bad things about dead code. Dead code is pretty dead, you can get rid of them. So here, what are the dead code you have? I want to keep at least somewhat engaged, so see whether you can find my dead code. Why? Yeah. I got rid of y's use now, I don't need it. I can just get rid of that, and then I can even get rid of allocating y. So I got rid of both instruction and some memory allocated or register that used to keep that value here. Another interesting thing you can do is loop invariant code motion, because loops are very important. Most of the execution time is mainly inside loops. So if you can get something out of the loops, it's really good. We talked about that previously. But you have to worry about basically 2 things. One thing is that when you move too many things out of the loops, you have to keep all those values in registers. So that means you need more registers inside the loop. Second thing is when you execute that, you have to make sure that it has the same behavior as when you run the program. How about in special cases if the loop never gets executed? So I did something which in fact, so here's, okay, first let's look at this. What are the loop invariant expressions in here? Hmm? 4 times A divided by B. Yes, okay, good. I just moved up there. So I did that. So, but why am I really wrong? Why wouldn't the compiler do this? Give me a case that this would change the program behavior. Four times A overflow, yeah, that can happen. That's one case, but there's something that can happen. Overflow happens on very large numbers, people don't care that much, but there's something that can happen a lot more.
If B is 0 and n is less than 0?
Exactly. When B is 0 and n is less than 0, I am going to have a divide by 0 error in here. Because I am going here dividing by 0, that would have never happened because the loop wouldn't have gotten executed. So normally when you do things like that in a loop, the compiler generates a place called a landing pad, which basically is checking that before you enter the loop, you check whether the loop will ever get executed, and then go to the landing pad, and then go to the loop. So the landing pad will be run only when the loop at least has one iteration running. And so you can move all those things in the landing pad. So here in C, there's no landing pad. The code generated probably would have. And so I did something that is, you would see, in fact, the optimized code I didn't do that. So GCC minus 04 is smart enough not to do this. So then there's another type of strength reduction, which is saying if I go like something like A times I, what I can do is just instead of doing A times I can basically make it at the first iteration, initialize it, and every time you can update the previous value. Okay, instead of A times I, the first time it's 0, and next time it will be T plus A. So I can keep updating that. Okay, so this is really great. I have less computation because now instead of multiply, I just made it add. But I have a lot of problems can happen here. First of all, I have now this one, I didn't have to keep this value anywhere, only when I needed it in here. In here, this value has to be valid throughout the entire loop because I keep updating that value. So I created another need for a register that before I only needed at that point. I calculated value, used it, but now the register has to be there throughout the program. So I created in there. Also, what I created is what we call a loop carried dependence. Every time you run iteration, you use the previous iteration's value. When we go into parallelizing loops, you suddenly realize that means I can't run them parallel. So this creates a huge problem in parallelization. So you do strength reduction or strength increase when you go to parallelization. You need to undo these things. So in here, one thing you can do is you look at something like U times I and say, wait a minute, I don't have to multiply by I because it goes U0 like this. And I can just allocate a value V and keep it updating by V. And then I did that. Just allocated a variable in here, allocated 0. And instead of this, I just basically put V times U. You see that? I just basically got rid of a multiplication and converted it into addition. But I paid some cost by, I need now an additional register that is true throughout the entire thing. Before, and I just could calculate that expression here. Okay? And the big thing, you get performance is register allocation. So most processors have very few registers. In fact, one big change that when you went from x86 to x86 64 is to get additional registers because registers are very important. And so what I will go through register allocation a little bit. So what happens is when you have a program, you have a control goes like this. So this control going, executing something that defines this variable x, defines variable y, and here you use variable x and variable y, and there are different paths the program can go. So there are two paths, this can merge in here, here you can expand in here. So this is kind of the flow of the program in a small part. So what you can say is this definition y is used here. So this value is live in between here because you can't get rid of it. When you define it, you have to keep it somewhere because somebody is going to use it. And this definition is used here. So when you define it, you have to be live in here. When you use this y, it's only used here. Nobody uses here, so this has to be live in here. Interesting thing about x is there are two definitions of x that might be used here. And this definition might be used here or here. So you put all this into what we call one web of this, because these two definitions, either one of them will be used here. This definition will be used either one over here. So this value has to be lived in here, kept somewhere. So then what we say is this is S1, we give names to these of them. It's S1, S2, somebody has to keep this value, S2 keeps this value, S3 keeps this value, S4 this value. The interesting thing is how many registers you need to keep all those values. Okay, that's what the entire thing about register allocation. So what you do is this really cute mapping of this into a nice theoretical problem. So what you can say is each of these regions, we make it a vertex of a graph, and then if these regions overlap, then we create an edge. S1 and S2 overlaps. That means you can't use the same register to keep both S1 and S2, because before S1 is finished using, S2 has to get created. Okay, there's overlap in here. So we create an edge in here. Okay. S2 and S3, so S2 and S3 overlaps here, because at this point both value S2 and S3 has to be kept. So I created an edge in here. Okay, so I created an edge. Every time I say those two values need separate registers, I can't keep the same register. And of course S3 and S4, S3 is here, S4 can be in the same register. Okay, so there's no edge here. Or S1 and S4 can be in the same register, or S2 and S4 can be in the same register. Okay, because they are not live at the same time. They are live at the different time of the program execution. And now, what you can do is, you have a graph, you have edges, and there's this very famous problem called graph coloring problem. How we have heard of graph coloring problem? Okay, good. So what happens is now we can figure out how many colors need to color this graph. And that is the number of colors is the number of registers you need. So if you have a graph like this, how many graph like this with no edges, you can color it with one color. That means there's nothing. How many colors for this one? 2 colors. How many colors for this one? People say 2 colors. Yes, you can color it with 2 colors. How many colors for this one? 3 colorable. So there's all these algorithms. You can go graph color and say, now you can say by coloring this, how many registers I need. And the interesting is, if you need more colors than the registers you have, that means you can't register allocate. And at that point, you need too many things to keep. You don't have that many registers. And at that point, what you're going to do is spill. That means you take edge and say, aha, I can't keep both of these guys in the same. I will take one out. Some vertex out and say this vertex can't be in there because I can't put it into register, and I spill this out. And you can recolor the graph, so you can spill it, and of course spilling is costly because now instead of having that value in the register, it's in the memory. And so every time you need it, you have to bring it back, put it out, send it back, so it's going to be expensive. So the nice thing is to see how much you can keep in the register. So in here, so I have enough registers for this program, so I found registers for all these things instead of putting it in memory. And now this is, can't see register allocation in a pseudo C code. So this is the kind of the optimized code, and this is the generated basically O4 of the original program generated. But in here I moved this one up. I said, but in this one, actually the division didn't get moved up. So IDIV actually is inside the loop because it realized you can't do that. But interestingly, it moved the multiplication out. So it didn't care about the overflow. It says, overflow, it can happen overflow, but it worried more about divide by 0. Okay? Any questions so far? So here's the optimized code, and if you run it, it's like 8 seconds versus 54 seconds. Just GCC O0, GCC OS. So it will produce a very compact optimized code. So the key thing is, what stops these optimizations? The key thing is you have to guarantee when you optimize all the that the programs are equivalent from unoptimized to optimized for all the valid inputs, all the valid execution, and all valid architectures that you are supposed to run. You have to do the same thing, otherwise it's not a good optimizer if it does different things to code. So there are a lot of things that means you have to be very conservative in many cases. So you have to understand both control flow and data accesses. and make sure that you understand them. And if any of them, the compile time analysis cannot understand, the compiler gives up very fast. So the thing is, most of the time, if the information is not available, compiler will reduce the scope of the region it's doing the transformation. Say, okay, at this point, I don't know beyond that. So I can only do a small amount of transformations here. Or reduce the aggressiveness of transformations. And sometimes just completely leave code alone as it is, because it couldn't, even though things you know, no sane programmer would do, and of course your code will never do, the compiler has to assume if it is a valid C semantics, it might happen. Even though it may, I mean, some of them look really crazy. If it is a valid possible way of doing it, compiler has to worry about it and not do that. So you have to be careful on that. So first of all, control flow. That means it has to work on all possible paths of the program when you execute that. And the way you look at it is you can add this call graphs when the high level, all the calls in here, and control flow graphs within the method or a function, how control goes around. And what makes it hard for compiler to analyze this? Bunch of things. If you have function pointers, you probably haven't done function pointers, but if you have function pointers in there, compiler can't say, oops, I don't know where it's going. I have to be very careful. Indirect branches. So I keep address in somewhere, and I branch to that. I don't know where it's going. Something like computed gotos is similar to that. Large switch statements. It's the spaghetti code. You have no idea where you're going to end up, and compiler assume it can get anywhere in the switch statement. Even though you might know some order of going through that, it doesn't work. If you have loops with exits and breaks and very complex things in there, compilers sometimes have to give up. When the loop bounds are unknown, you assume it could be anything. Whereas when loop bounds are known, you can, as you saw in the first set of examples, you can take advantages a lot more, and you can do a lot more aggressive things, or not care about cases, because I know that. But in these unknown loop bounds, you have to be a lot more careful on that. And conditions where branch is not analyzable. So if you have branch condition, if you don't know what's happening in the branch, I might not be able to take advantages or think how to do the branch well. So those are the things that I have to worry about. The other thing is data accessors. So that means who else can read and write the data. So I am touching on the data item. And I need to know that between the 2 points I am looking at the data, nobody else can go and muck with my data or use my data. Because when I look at the data item as something, I want to make sure that's the only way that data can be accessed. Because as you know, most of the things are in memory. So normally compiler calculate is this called def use change. So define to use. So you can say that thing get defined here is going to get used here. And nothing comes in between that. And that information is that's how the compiler came. There's another thing called dependence vectors. We might talk about a little bit about that when we go into parallel execution. So what makes it very hard for compiler to analyze this? For example, address taken variables. So if you write and hack with C, you can say, okay, there's a variable here, I'm taking the address of that. Suddenly, that means somebody else has the address to the variable. So that means anybody else suddenly can jump in and overwrite you, and there's a lot of possibilities of doing that. And suddenly compiler says, wait a minute, that variable, even though I know I assign the variable here, I'm using it here, in between, somebody else might touch it, even though it might not use the same name, because somebody else has the address to that. Okay, so that's a hard thing. Global variable sometimes. Because between functions, I don't know, some other function might go and change it. Parameters are really hard. Like for example, remember in our program when we had something like copying same array to the same, even though parameters say x and y, I might send the same or overlapping regions into two different parameters, even though it looks like two different names. They're not two different things, they're actually overlapping at some point. And so you have to assume, even if you have parameters, two different parameters point into memory, they might be the same thing. And that's the worst case. A lot of times nobody does that. Nobody gives the same things in multiple names. But it's possible. If it is possible, compilers deal with it. Either it has to generate code to test all these cases. Is it overlapping? If not, do something. If it is overlapping, do something slower. Like the code we showed when you are vectorizing. It created like this huge number of different cases. But you can't, unless you do something like that, you can't optimize. And complex programs, very hard to do that. A lot of times pointers create issues in here. Because the problem with the pointers is what we call point aliasing, because pointers, you can add any value to a pointer. And you have no idea if you had a very large value, it can be anywhere in memory. Because if you have a pointer, you have a point into memory. You can add anything, subtract anything. You can basically, the world is yours. And C gives you this ability to go all over the world and kind of muck with the world. And some programs do that. And so the compiler said, oh, it's a pointer. I don't know where it is. I just have to leave it alone. Because some guy, 0.001% of the world programmers will do something crazy, and everybody has to pay the price. So this is what makes programming hard. And the final thing is there's a thing called a volatile types. When you go to parallel programming, you realize because normally compilers keep a value, normal values are in the memory. Compiler can pick the value into register and keep operating in the register and at some point put it back to memory. But if you're running a parallel program, somebody else might want to look at that value. And when it is in register, you don't have that value in the right place. It's somewhere else, so you get a stale copy because you have moved it. Volatile says, look, you have to always keep it in memory. You can't take it out. You can just modify it, but you can't move it somewhere else, faster place to do things to it because somebody else might be looking at it. And so what that means is compilers give up its hands and say, look, I can't do anything. So we are a little bit early. I have this yet another huge section in here. Oh, okay, we have to go to this thing. Good. I think now we are going to go about and see how you guys did in the class exam. Okay. And I am seeing it for the first time, and it looks really nice. Where is it? Where do you plug this in? Where do you plug this in? So okay, so here is the distribution of the India. This was not an easy exam. And in fact, we compared how you guys did to last year, and you guys have done a lot better than I think the first exam in last year. So basically, we have median about 70 somewhere here, and a nice tight grouping in here. So which is really good. And so what we have is we have the exams back. Take a look, and I think okay.
I'd like to make one comment about
Sure.
how my grade is.
Okay, sure.
Misunderstanding.
Yeah.
So, not surprisingly, I graded the problem on the cache oblivious algorithm. Okay, doing the recursion tree. There was a common mistake that many people made, which was kind of which I wanted to explain why it's wrong. Because so many people made this mistake. They got it almost all right, and then they made this mistake. So it's basically an understanding of recurrence. So the recurrence, as I recall, was Q of R is equal to square root of R over B if square root of R is less than C M, for seed, et cetera, okay? And then otherwise, it was 2 Q of R over 2 plus theta 1, okay? Now, what people did in their recursion tree, first of all, some people didn't recognize that what goes in the recursion tree is this value, okay, the number of cache misses. So the recursion tree is going to look like theta 1, or you can leave out the thetas if you want to put them in at the end, theta 1, et cetera. So many people got this. And then the question is, well, what happens when it hits the leaf? Okay? So when it hits a leaf, many people correctly got that you can't mess around with constants if they're in the, you have to be very careful with constants if they're in an exponent, that you hit the leaf when you are when square root of r becomes less than c over m, in which case the cost is going to be square root of r over b. So what they did is, the incorrect thing was they put square root of r over b here. Why is that wrong? It's the wrong r, right? Move this out of the way so people can see. Okay, it's the wrong r. This r is the r here on the right-hand side. It's not the one here. It's the r, if r is sufficiently small, that's the value you're taking. But we're expanding an r from the top here. So what's the value that should go here? Okay, Cm is the value that should go here. Okay? The value that should go here is Cm. Yes?
For everybody and for convention, not to have two r's actually on the right side.
Yeah.
And then instead of having two r's that are written the same but are spoken differently.
Well, when you say, what do you mean? This is, there's an r here.
And it's different from the other r's.
No, it's the same r. The question is, r is a variable. So it'd be nice if the r were constant, but it's not. It's a variable. And so the point is, the point where you plug it in here, you've got to plug in not the variable, you've got to plug in the value.
You could just say for r,
I mean, it's a variable. You have to plug in the value of the variable at this point if you're going to solve the recurrence. Putting in r here, we're trying to say this whole thing is q of r. And we started out, if we did the development of the tree, which is the safest thing to do, you get theta 1 plus q of r over 2. And you keep going down until your value for r satisfies this condition. At that point, what's the value for r? Okay? You can't then say it's the same r that you started with. It's not this r. And that's because r is a variable, not because of anything else. R is a variable, and we're using the r. This is a question of understanding of the recurrence. So, so in any case, that was a common mistake that people made. The other minor error that people made on that problem, that most people made, was in describing where do you get this recurrence, they left out the fact is, why is it going to be square root of r over b? It's really because NA is approximately NB. Because the way that the code works, we're keeping NA and NB to within a factor of 2 of each other. Okay? And so if you didn't mention that, you lost a point. It wasn't a big deal. But, but many people didn't neglect that very important statement. Overall, people did very well on this problem. Overall, you'll see people got a lot of partial credit on it.